Hi everyone, I'm Tim Kington and this is Coding is for the Birds. This video goes along with the main sequence Java for Beginners videos. A lot of people when they're learning to program just want to be able to make things happen and write some basic code, and that sequence of videos will cover everything you need to do that. If you want to be a strong developer though, you really need to understand what's going on under the covers. And so I'm going to be doing a series of these deep dive videos to accompany some of the videos in the main playlist. Today we're going to be digging into primitive types in Java. In the main video, we talked about some of the primitive types in Java, and we looked at how to read some input from the user. Let's look at the rest of the primitive types we have available. We have several integer types of different sizes. So let's print their ranges out. There are predefined constants in Java for the minimum and maximum value for each of these types. And the types are called byte, short, int, and long. Now, the capitalized versions of these are a little different than the primitive type versions. We're not going to worry about that too much right now. We'll talk about that a little bit later on. So the primitive types are lowercase, but we do have these wrapper classes that hold some information and methods that are useful with these types. And that's all I'm going to say about that for the moment. But if we print this out, we'll be able to see what the ranges are for each of these types. All right, so the byte type goes from -128 to 127. Short can hold numbers from -32768 to 32767. Integers go from -2 billion to about 2 billion. And then longs go from -9 exillion to 9 exillion. These can hold very large numbers. Why is that? Well, it comes down to the way that we store numbers inside the computer, and we'll take a look at the details of that shortly. We also have a couple of floating point types. We have one called float that I didn't mention in the main video. And we have double, which we did mention. And these can hold numbers with decimal parts to them. And they also can keep track of exponents, so they can hold numbers that get pretty large. So the minimum float is 1.4 times 10 to the -45th. So that's a pretty large negative number. And then we can hold a number that is a 3 with some other digits, but basically it would be a 3 followed by 38 zeros. So some fairly large numbers. We have a char type that can hold a single character. Single characters in Java are wrapped with single quotes. So this is not a string. I cannot put 2 letters in here. If single quotes surround the value, then it's a character. And there is a character primitive type for that. And then we have our Boolean type, which we already discussed. It can hold a true-false value. So these are the primitive types we have available in Java. The integer types will work just like the int type, except that the range of values they can hold is different, and the types of literals in Java will default to integer, and that can cause issues in some cases. So we could say something like byte, my byte, equals 12. In this case, Java's smart enough to figure out that 12 will fit into a byte. If we put in a number that's too large for a byte, then we're going to get an error. Bytes only go up to 127, so the compiler is going to tell us this won't work. If we had made this a short, then this would be fine. And once we go past 65535, we'll get a similar error. And then longs can hold much larger numbers. But when we enter a number that's larger than what we can hold inside an integer, we're going to get an error from the compiler. That's because the compiler is going to assume that any whole number we see in the code is an integer constant. If we want it to be a long, we need to put an L on the end of it to tell the compiler that this is a long, this constant is a long. We can do that with a capital L or a small l. I prefer the capital L because the small l looks kind of like a 1 and you might miss that, but the capital L stands out more when you're reading the code. When we're using floating point numbers in our code, we can write them in decimal form as we did earlier. But we can also use scientific notation. And here we're going to have the same sort of issue we had with the integer types. The compiler is assuming that any floating point constants we see in the code are doubles, and it will not be able to convert those to floats automatically. If we want this to be treated as a float, we need to put an F after it. And we can do that. It's pretty rare that we would want to use a float in the first place because usually we're not worried about memory, and doubles have more precision. So we would just normally use doubles, and it'd be kind of rare to use a float. We can also use scientific notation when we're defining floating point numbers in our code. So let's go ahead and change this to a double. And we could say this is 1.34 times 10 to the third power. So this is actually going to be the number 1340. We can do this with a negative exponent as well. And this will be 0.00134, I believe. We can always print this out and see what it looks like. Yeah, so you can see that the decimal place was moved 3 places to the left here, so we wind up with 0.00134. Why do these integer types have such strange ranges? Well, that comes down to the way we actually store the data inside the computer. Bytes are using a single byte of memory, which has 8 bits in it. Each bit is a 1 or a 0. So when we store 0 inside the computer, it's actually 8 bits that are all 0. And then we count up from there using binary. So if the least significant bit is a 1, then this is 1. If we set a higher bit, say this one, this would be equal to 8. And we're just using normal binary numbers here. So this is the same thing you probably have seen back in math class a long time ago. So the largest value we're going to be able to store in a byte would be all 1s. If our bytes were unsigned and we just used normal binary counting like we did in math class, then this would be 255. But Java does not have unsigned types. Java sets aside this first bit as a signed bit. So we don't really want this one to be a 1. Making that a 1 makes the number negative. The largest number that we can represent in Java is going to be 127. So the first bit in our byte is a 0, which means it's positive, and all the other bits will be turned on, and that's the largest number that we can represent inside of a byte. When the signed bit is 1, then the number is negative. Java uses what's called 2's complement to handle negative numbers. If we want to create the negative version of a number, let's say we wanted to do -1, we would flip all the bits that we had in +1. So we'll take these last 7 bits that represent the number. Really, these bits are split off in our numbers. So we're going to flip the bits that represent 1 here. And then we add 1 to this number. And so that last 0 is going to get turned into a 1. And we're going to set the sign bit to say that this number is negative. And this will be -1. We can do this for 2 and 3 and 4 and go on. And what we'll find is that we're sort of counting backward in binary. So -2 will have a 0 here. And then -3 will have this number -1 as its numeric component. If we flip 127, we'll have our sign bit turned on for a negative number. All of these bits will be 0s because we flip the positive numbers bits. And then we add 1 to this. So this is -127. You'll see that we have one more number. We can count down one further here. We could turn this into a 0. And that's actually going to be -128. This number does not have a corresponding positive value. There's no way to store +128 in a byte. So this is really how we're storing the data. And the reason that we have more negative numbers than positive is that we need to be able to store 0. So we had to decide we could store 127 positive numbers and 128 negative ones, or vice versa. And using 2's complement arithmetic, we wind up having one more negative number than positive number. The same basic thing is happening with our short, our integer, and our long types. They just have more bits, so they can store larger numbers. Our short is going to be a 16-bit value. Our integer is 32 bits, and our long is 64. So I'm not going to try to write out the numbers and do any of those calculations in my head, but they follow this same pattern. They have a sign bit at the top, and then the rest of their bits are devoted to the numeric value, and they will always be able to represent one more negative number than positive number. So you can see this goes down to 32768. Positive numbers only go up to 32767. And the same is true for the int and the long ranges. We can see that this is how things work if we cause our variables to overflow. So if I assign an integer the maximum value that an integer can hold, that'll be this number here. And then we add 1 to it. And we print it out. What will happen is this is going to wrap around to a negative number. And it's actually going to print the largest negative number that an integer can hold. So it's this value here. What happened here? Well, if we had done this with a byte, we would have started with this value. This is the largest value that a byte can hold. All of the numeric bits are 1 and our sign bit is 0. If we added 1 to this in binary and we treat all of these bits as part of the number, the next binary number up is this one. We would have a 1 in the first bit and a bunch of zeros after that. And that's what the VM and the CPU are doing when we add 1 to the number. So with the integer, we had the same thing happen. Our largest possible integer value is a 0 sign bit followed by 31 ones. When we add 1 to it, we get a number that is 1 for the sign bit and 31 zeros. And that's going to be the lowest possible integer that we can represent. So we wrapped around and we wound up with a negative number. If we subtract 1 from that, then we'll wrap around again and wind up back at the largest possible integer. So when our virtual machine's doing arithmetic, it is not doing any bounds checking on our numbers. If we go to a number that's larger than the type can hold, it will wrap around into the negative numbers. If we're in the negative numbers and we subtract from it, and we get to a negative number too large to be held, we'll wrap around back into the positive numbers. If we add more than 1 here, we will go farther into the negative numbers. So if we added, say, 3 here, then the negative number that we get is not quite as large as the largest negative number we could hold, right? This ends with 648. This ends with 646. So we have wrapped around and then turned on some of these other bits in our negative number. Floating point numbers are also stored as 1s and 0s. Really everything in the computer is stored as 1s and 0s. But the format is different. If we're looking at a 32-bit float, so the float type in Java, we have 1 sign bit. We have 8 bits that represent the exponent. And then the rest of the bits are used to represent what's called the significand, which is basically the base. This is pretty much writing a number in scientific notation, but in binary, so in base 2, instead of the base 10 that we're familiar with. When we started with 32 bits, we've used up 9 of them so far. So we have 23 left. But we do something clever to really squeeze an extra bit out of the significand. We'll look at how that works in a second. First, let's look at some scientific notation in decimal just to sort of refresh what that is. So we can write a number as, say, 1.34 times 10 to the 6th power, right? And this would mean we start with this number, and then we raise it, or we multiply by 10 to a certain power, and that has the effect of shifting our decimal place. So this would really be number 134, and we've shifted the decimal to the right 6 times. So we've shifted it twice so far, so 4 more, and we'd wind up with this number. So it'd be 1.3 million. We could do the same thing in binary. So we could say something like 1001 times 2 to some power. All right, and we're not really used to writing decimal numbers in binary, but we could. Something like this. So this is 9. And then we have a decimal point. And then the first decimal digit in binary would be 1/2. So this is worth a half. And the next digit would be a 4th and then an 8th. So this is a half plus an 8th. So this is actually 9.625 is what we're representing here. And then we can use a binary exponent to shift our decimal place in exactly the same way that we do in normal scientific notation. So this would mean move our decimal place 3 places to the right. So this would really be 1001, 101. Now, it wouldn't make sense here to do this because we could have represented this as a whole number. So let's make our exponent a little bigger. Maybe it was to the 5th power, so we would have 2 extra zeros on the end here. This is essentially what we're doing when we represent a floating point number in binary. We're going to have a base. Now, our base is going to be a whole number, and then we're going to have a power that will represent where the decimal place is going to go within that number. When we represent a floating point number, then we're going to wind up with these 3 pieces. So if it's a positive number, our sign bit would be 0. Our exponent is a byte, it's 8 bits. It has almost the same range as a byte in Java, so it can't quite go from minus 128 to positive 127 because there's some values set aside for special numbers. But it more or less has that range. It's something like minus 126 to plus 125 or something like that. And then we have the significand. So maybe our exponent is, say, 3, 0, 1, 1. There would really be more zeros here. Something like this. And then we could have our significand, which would be the base here. Basically, it's the number that we're going to raise to some binary power. So then you have a bunch of binary digits out here that would, represent the number that we're going to start with. We get 1 extra bit here somehow magically, right? We really only have 23 bits left in our 32-bit number, but somehow our significand is 24 bits. The reason for that is that our significand is always going to start with a 1 bit. If you think about it, if we had a number here that did not, so let's take this example and say that our base was 01001 .101 times 2 to the 5th. Well, this leading 0 is not interesting, right? It doesn't add anything to the final result. So our significand should never start with a 0. It always starts with a 1. And that means that we don't actually need to represent it here. It's assumed that it starts with 1. So we don't have to store that bit anywhere. Everyone that's dealing with these floating point numbers just knows that this starts with a 1. So if the significand looked like this, we would know that it really has this hidden 1 on the front of it. And I didn't really write out the right number of bits here. This should be 23 bits plus the 1 bit that's implied. So your floating point numbers are represented something like this. And we can do exactly the same thing for a double. A double just has more bits. So it's 1 bit for the sign. I think it's 11 bits for the exponent. And that leaves us with 52 actual bits for the significand, but we use the implied bit to make it 53. So we can represent a wider range of numbers there. These floating point numbers also have a few special values. There's a positive and negative version of 0, and then positive and negative infinity can be represented. So if you do a calculation that overflows and makes a number that's too large to store, it will actually come out as infinity. You can use that in your code as well. We can say double.infinity. Here we go, positive infinity and negative infinity. And if you print these out, then it actually prints infinity on the screen, which is pretty surprising the first time you run into it. So yeah, we ran into infinity. There are also some numbers called subnormal numbers that can be represented that are really smaller than the ones that fit into this scheme. We don't really care about those right now, but it does make the doubles perform a little better if you kind of screw up. If you're having an underflow and you're getting a number that's too small to really represent properly, it still sort of partially represents it and gives you a lower precision version of that number. So doubles are actually fairly complicated. We can see that doubles are stored something like this if we try certain operations with them in our code. So we can represent things with fractional parts that can be represented by powers of 2 exactly. Those numbers are represented exactly. So something like 2.75, that's a half plus a fourth. We could add in another eighth, so 2.875. This is perfectly representable. But most numbers can't be represented exactly. We can see some problems if we use floats especially. So let's say that we had 21.4 and then 5 zeros and a 1, and we print that out, and that's a float rather than a double. A float doesn't have enough precision to really hold this number, because the base is not long enough to hold both the 20 and this bit out here at the end that we need to represent the 1. So you're going to see just 21.4. If we get rid of one of these zeros, then the float gets a little closer, but it gives us a 2 at the end instead of a 1. So you can see it did a little bit better job, but it's not exactly representing this number. This is one of the reasons that you should never use doubles or floats to represent money. There's a class in Java called Big Decimal, and that is appropriate for money. It will never lose precision. It will just keep using more and more memory and always represent your numbers exactly. So you should use that if you're ever doing any kind of important financial calculations. Most of the time, doubles are okay if we're doing something with floating point math, and we don't really care about the precision out here at the end. We just want to get a number that's very close to the right answer. Chars in Java are the only unsigned type. Char is actually a 16-bit type, but there is no sign bit. So its range is actually 0 to 65535. A char represents a Unicode code point, and that means that Java strings can contain text in any language or any character set. So we can have Chinese characters, English alphabet, emojis, really anything that's represented in the Unicode standard. And then Booleans are pretty uninteresting. They just store a true-false value, so there's not much to say there. Last I remember, the Java VM spec did not say how Booleans had to be stored in memory. So it may be different on different platforms. Some platforms may pack the bits, so you could actually store 8 Booleans inside a single byte of memory if you use each bit as a true-false value. But I think most of the implementations I've seen use a byte to store a Boolean, and it's either equal to 0 or 1. Okay, so there's a deep dive into Java primitive types. Hopefully that's cleared up questions about some weird things your code has been doing. Maybe you were doing some calculations with doubles and got weird results, or you did something with integers and suddenly your results were negative. I'm planning to do more of these deep dive videos. If there are any topics related to Java or the virtual machine that you'd be interested in learning more about, let me know in the comments. Don't forget to like and subscribe.